By now, almost everyone with an internet connection has seen the footage. It is the viral clip of the year. A massive UPS cargo plane climbing out of Louisville, Kentucky. And then, the impossible happens. The number one engine, a 4-ton piece of machinery, simply drops off the wing. It falls like a stone, while the plane banks violently to the left and disappears behind the tree line. For the last month, the internet has been flooded with theories. Maintenance failure, rust, metal fatigue. The comment section is full of anger. People are asking, how could the bolts just snap? Why didn't they hold? But today, on the Air Debrief, we are going to tell you the truth that the news channels are missing. The bolts didn't fail because they were weak. They failed because they were designed to fail. What you are looking at is not a malfunction. It is a safety feature working exactly as intended. The engine wasn't lost. It was sacrificed. Welcome to the investigation of UPS Flight 2976. Tonight, we are going to explore the darkest paradox in aviation engineering. The moment when a mechanism designed to save a plane becomes the very thing that destroys it. To understand why Flight 2976 crashed, we first have to understand the machine, the McDonnell Douglas MD-11. It is a beast of the skies. And hanging under its wings are the General Electric CF680C2 engines. Each engine weighs nearly 10,000 pounds, roughly the weight of 2 large pickup trucks. Now, imagine the force these engines generate at takeoff. Nearly 60,000 pounds of thrust, pushing the aircraft forward, vibrating, twisting, and pulling at the wing. Here is the secret that most passengers never think about. How do you attach a 10,000-pound vibrating monster to a fuel-filled wing without tearing it apart? You use something called a pylon assembly, and inside this pylon, holding everything together, are specific attachment points. These are not just ordinary bolts. They are what engineers call fuse pins. Think of the fuse in your home's electrical box. When the current gets too high, the fuse blows to save the house from burning down. These steel pins work the same way. They are structural fuses. They are hollow. They are engineered with a specific shear neck, a calculated weak point. Why? Because of the nightmare scenario. A seized bearing or extreme vibration. If an engine seizes violently mid-flight, the torque and vibration could transmit directly into the wing structure. Inside that wing is the wing box, essentially a giant tank full of Jet A fuel. If the engine rips the wing box open, you have a massive fuel spill, a spark, and a mid-air explosion. Everyone dies. So, McDonnell Douglas engineers made a choice. They decided, if the forces get too extreme, we will sacrifice the engine to save the wing. This is the clean break philosophy. The pins shear. The engine separates cleanly. The wing stays sealed. The plane glides to a landing. That is the theory. That is how it works in the simulation. But on November 4th, 2025, over the skies of Louisville, physics decided to rewrite the rulebook. Let's reconstruct the sequence of events. UPS Flight 2976 is passing 1,000 feet. The pilots are retracting the landing gear. Suddenly, a catastrophic vibration hits the airframe. We suspect a fan blade failure or a compressor stall created an imbalance so severe that it exceeded the load limit of the fuse pins instantly. Snap, snap, snap. In less than a second, the engine is free. Here is the tragedy. When the fuse pins shear, the engine is supposed to drop down and away. But gravity isn't the only force at play here. The engine is still producing thrust. The plane is moving forward at 160 knots. The angle of attack is high. Instead of dropping, the engine tumbles. It effectively vaults over the wing's leading edge. It impacts the leading edge. It slices through the aluminum skin like a guillotine. And sitting right there, running along the front of the wing, are the hydraulic lines for System 1 and System 3. In an instant, the aircraft bleeds out. High-pressure hydraulic fluid sprays into the slipstream. Why does this matter? Because of what those hydraulic lines control. This is the ghost of 1979. Just like the infamous American Airlines Flight 191 crash decades ago, the loss of hydraulic pressure caused a fatal chain reaction. The leading edge slats, those panels that extend from the front of the wing to generate extra lift at slow speeds, are held open by hydraulic pressure. When the lines were severed, the pressure vanished. The force of the air rushing over the wing simply pushed the slats back in. They retracted. On the right wing, the slats stayed open. On the left wing, the slats closed, and Flight 2976 effectively became two different airplanes welded together. Put yourself in that cockpit. You are the captain. You hear a bang. The plane shudders. You don't have a rear-view mirror. You can't see the wing. You don't know the engine is gone. You don't know the slats have retracted. All you know is that the world is tilting. This is called asymmetric lift. The right wing is flying happily, generating massive lift. The left wing has lost its engine, so it's lighter. But more importantly, because the slats retracted, it has entered a stall. The smooth airflow over the left wing has broken down into turbulence. It stopped flying. One wing wants to go up. The other wants to drop. The result is an uncontrollable, violent roll to the left. The pilots did everything right. Data from the flight recorder shows they applied full right aileron and full right rudder. They were fighting for their lives. But at this low speed, with the left wing fully stalled, the aileron simply didn't have enough authority to counter the roll. Physics had already cast its vote. From the moment the slats retracted, the aircraft was undeniably unflyable. Greg Biffle died fighting a mental illusion. The pilots of UPS 2976 died fighting a mathematical certainty. History is a circle. 46 years ago, a DC-10 took off from Chicago. Its engine separated, its slats retracted, it rolled over and killed everyone on board. The MD-11 is the direct descendant of the DC-10. After 1979, McDonnell Douglas redesigned the slat system to mechanically lock them in place, even if hydraulics failed. So, the burning question for the NTSB investigators right now is, why did the lock fail on UPS 2976? Did the violence of the engine impact shatter the locking mechanism? Or was there a maintenance oversight in the years leading up to 2025? This investigation will likely focus on the fatigue life of those fuse pins. Were they inspected properly? Or did micro cracks go unnoticed until the load became too great? Until the final report is released, the entire MD-11 fleet remains under a cloud of suspicion. Furthermore, the NTSB's preliminary report released this morning has shifted focus to a critical failure point, the slat actuation mechanism. Following the historic DC-10 crash in 1979, McDonnell Douglas mandated the installation of mechanical locks to prevent slats from retracting during hydraulic failure. The fact that UPS 2976 suffered this exact uncommanded retraction suggests a terrifying reality: uncontained impact energy. Investigators believe the sheer kinetic energy of the rebounding engine shattered the mechanical locks instantly, bypassing decades of safety redundancies. Data from the flight data recorder reveals the aircraft reached V2, or takeoff safety speed, but immediately decayed to V2 minus 10 knots on the left wing due to the massive drag penalty. Crucially, the stick shaker stall warning only activated 3 seconds before impact, too late for the crew to diagnose the split flap asymmetry at an altitude below 500 feet. In response, the FAA has just issued an emergency airworthiness directive requiring immediate ultrasonic inspections of all CF6 engine pylons on the global MD-11 fleet. Any fuse pins showing fatigue cracking exceeding 0.05 inches must be replaced before further flight. This proves that Flight 2976 wasn't just an accident, it was a stress test that the airframe failed to pass. Aviation safety is a game of trade-offs. We install fuse pins to prevent a fuel tank explosion. We accept the risk of a lost engine to avoid the certainty of a burning wing. In 99 out of 100 cases, this design saves lives. But on Flight 2976, the dice rolled the wrong way. The safety feature worked perfectly, but the chaos of the real world, the trajectory, the impact, the hydraulics turned a survival mechanism into a death sentence. 2025 ends with a lesson in humility. Whether you are a racing legend flying a private jet or a professional crew in a heavy freighter, you are always just one sheared bolt or one sensory illusion away from disaster. The machine doesn't care who you are, it only cares about the laws of physics. Fly safe, trust your training, but respect the machine. For the Air Debrief, I'm your host. See you in 2026.